In this video, we're going to learn how to tell the direction of the magnetic force vector with the right-hand rule. So if you're in a trigonometry-based course, you have probably seen this. If you're in a calculus-based course, you've seen this. You've also seen this. This is the cross product, where this is the magnitude of the cross product. This is involved in the definition. So you can get the direction out of the cross product just by calculus. I and many other people think it's probably just easier and more straightforward to not deal with the vector product explicitly at this level, but deal with the magnitude and determine the direction with the right-hand rule. So no matter which course you're in, this is usually going to be the method you use to determine the force vector. Now remember, the force is perpendicular to both the velocity and the magnetic field. So if you have the velocity vector and the magnetic field vector in the same plane, in this case, that's the plane of the paper, right? The velocity vector is in the plane of the paper, the magnetic field vector is in the plane of the paper. Then the only option for mutual perpendicularity is for the force vector to come out of the page or to go into the page. So we need to develop some terminology to talk about, or not talk about it, we need to develop some graphics to show that. So for the purposes of our course, this is going to represent a vector going into the page. I like to think about it as the backside of an arrow. So if you fire an arrow, you're kind of looking at the feathers at the back of it, or maybe the notch where the string was as it's flying away from you. So we interpret this as just a vector like this, but directed into the page. We're going to interpret this symbol as a vector directed out of the page. If you again think of it like an arrow, an actual arrow, this may be the point of the arrow as it's coming towards you. So this is going to represent a vector into the page. This will represent a vector out of the page. So if I'm going to determine the magnetic force vector here, that is the direction, the magnitude is given here, I am going to do the following right-hand rule. Now, I'm going to give you my favorite right-hand rule. If you're in my class and we're still using the OpenStax textbook, they use a different right-hand rule. There are even more right-hand rules. There are at least 3 that I know of. I do not like the one in your textbook, but if you like it, use it. If it works for you, then use it. And just ignore everything I'm about to say. There's one where you do this with your fingers to create a coordinate system. If you like that one, use it. That's totally fine. The right-hand rules are all going to give you the same answer, but here's the one I like. Now, remember, order matters here. Order matters. The 2 components in this expression that are vectors are the velocity and the magnetic field. In this expression, they're not vectors. This is a speed and the magnitude of the field. But really, we know that this comes from a velocity. And it's obvious in this expression, but if we're not using this, if we're just looking at this, the 2 vectors here are v and b, and I'm going to have to keep them in this order. This is actually really critical to how the right-hand rule works. And so the right-hand rule is this. I'm going to take my fingers, and for the purposes of this, we're going to let my thumb not be a finger. There are fingers, and then there's a thumb, and they're not the same. Now, of course, in real life, all thumbs are fingers, right? The classic example. But for the purposes of this, these are going to be my fingers, and this is going to be my thumb, which I'm not going to consider to be a finger. So here's how it works. First step, first vector here is v. I'm going to take my fingers and point them in the direction of v, so just along that line, okay? Once I have done that, I'm going to look at the next vector, and I'm going to bend or curl my fingers toward that vector, or in the direction of that vector, right? So if I'm just looking at these vectors, if v is here, toward b would be this way. So my fingers only bend in one direction, right? I can't bend them back like that very much. I can bend them like that. I can't bend them back. And so when I say bend my fingers in the direction towards b, what that has to look like in this case is if I put my fingers in V, well, I've got to turn my hand and I see where B is, and I can curl my fingers in the direction of B. All right, so stick my fingers in the direction of V and then curl them in the direction of V. Now, I'm probably going to have to reorient my hand a lot to do that. So after I do V here, I've got to look at B and figure out how do I need to turn my hand to do that. And in this case, I turn it sideways like this, and I curl it like that, right? So now my hand, it's hard to see on the screen, looks like this. If I turn it just a little bit, it looks like this. Now, third step, stick out my thumb, right? And you see that my thumb is now pointing into the page. So fingers in the direction of V, curl them in the direction of B, and then stick out my thumb. And right as I have it here, fingers in the direction of V, curl them into B, stick out my thumb. It's going into the page. And you might think, oh, well, great, I'm done. Well, the pitfall here is we've got a charge. And this charge can be positive or negative, and positives and negatives have to do with direction. You might think, well, this is a negative charge. Why does it have to do with direction? Because that will change the direction of the force. And so here I've taken the first step, fingers in the direction of V. Second step, curl them into B. Third step, stick out my thumb. The fourth step now is to check my charge. And if it's positive, do nothing. If it's negative, what I have to do then is invert my hand. Right? So originally, as I had this V to B, stick out my thumb is going into the page. If I find that my charge is positive, I do nothing. If I find that my charge is negative, I have to invert my hand, so what was once sticking into the page is now coming out of the page. And that now I'm done, and the direction of my thumb tells me the direction of the force. So notice, if this charge is positive, we'll say that this is some positive Q, right? If this is some positive Q, fingers in the direction of V, curl them into B, stick out my thumb, check the sign of my charge. Oh, it's positive, I do nothing. That means the force is directed into the page, and that will look like this. That will be the force on the particle. If, however, I'm going to have to do this in, I'm going to have to duplicate the blue color. If I find that my charge is negative for some negative Q, go through the same process, fingers in the direction of V, curl them towards B, stick out my thumb, check the sign of my charge. Oh, it's negative now. Invert my hand, and now I get the thumb coming out of the page. So if this charge is negative, I get that the force vector is coming out of the page. Okay, so here I've given you another situation. In this case, the velocity is coming out of the page. So what I want you to do is pause the video and do this twice. Do this for a positive charge and figure out what direction that is, and do it for a negative charge and figure out what direction that is. All right, I'm going to assume you paused the video and worked it out, so let's see what the answer is. So first step, fingers in the direction of the velocity. In this case, my velocity is headed into the page. So I'm going to put my fingers into the page, right? Just like that. So move my hand so you can see. And then I'm going to curl them into the direction of B. Well, B is down. So if you see, I'm going to curl my fingers, move my hand so you can see, move my thumb. I'm going to curl my fingers into the direction of B. Fingers into the page, curl them in the direction of B. That's step 2. Step 3 is stick out my thumb. And I have currently my thumb pointing to the left. Now, step 4, check the sign of my charge. Let's do the positive one first. Charge is positive, my thumb is to the left. What do? That's right, nothing. So if that's the case, I get that the force vector for the positive charge looks like that. This is the direction of the magnetic force on this particle. It's to the left. Now, of course, I would probably draw it on the particle if I were doing a free body diagram or something. But just to figure out how this is working, I get that the force is to the left. For the negative charge, you might be able to just say, okay, well, why don't I just reverse the direction of this? And you would be right, but let's go through it just to make sure we understand. Fingers in the direction of the velocity, just like this. There it is. That's into the page. Then curl them into the direction of the field. That's still down. I know this is hard to see. Into the page, curl them down, stick out my thumb. I again have a force going to the left, but now I check the sign of my charge. And this time my charge is negative. So I flip my hand over, I invert it, and I get a force moving to the, or pointing to the right. So, a couple things to get from that. Number one, a negative charge will experience an opposite force in that a negative charge that's moving in a magnetic field will experience an opposite force to an equivalent positive charge moving in the same direction in a magnetic field, right? So positive charge moving to the right, positive charge moving into the page gets a force to the right, negative charge moving into the page gets a force to the left, right? Also notice you can take that a little farther. If the negative charge is moving out of the page, it would get a force back to the left. But we've been saying that all semester, right? Positive charges moving in one direction act the same mathematically as negative charges moving in the other direction. That was one of the nice things about electricity that allowed us to characterize everything with positive charges instead of having to flip back and forth between positives and negatives. Because in the vast majority of practical situations, the charges are negative, but it's tiresome to keep track of the negative signs. So we always use positive charges. The fact that this works out here tells us a little, we can use the same tools. That is to say, we can keep it simple by using positive charges and not lose any of the physics on the way.